So I'm going to define what the dual of the linear program formulated in the standard form. So here's the LP. So it's minimize C transpose times X subject to A dot X equal to B, X greater or equal to 0. So this is the linear program formulated in the standard form. So by definition, the dual is maximize Y times B subject to Y times A less or equal to C transpose and Y unrestricted. Okay, so that's what they do. So this is called the primal, and this is called the dual. Okay, so the dual is a linear program because we're maximizing a linear form over linear inequality. So it's itself a linear program. And here in the primal X is a column vector, and the dual Y is a row vector. Okay, and X is restricted to be greater or equal to 0, but in the dual Y is unrestricted, meaning that it can take any values. Okay, and then the equality is replaced by inequality less or equal to. The unit cost in the primal goes down into this constraint, so it's part of the constraint, and the B moves up in the dual to be the some type of unit cost or profit or something like that. So this is the difference between the two. Now, there are many forms of the linear program. It doesn't have to be in standard form. Minimizing any linear form over linear constraints, that's a linear program. So what's a dual? You can get the dual just from this, from just remembering this. Many times in the literature you will see the dual defined like this. It's minimize C transpose X subject to A dot X greater or equal to B, X greater or equal to 0. That's a linear program defined by a set of inequalities. Now the dual to this is maximize Y times B, right? So B goes on the objective function, subject to YA, Y times A, less or equal to C transpose, and Y greater or equal to 0. So that's the dual. So this is a primal, and that's its dual. Okay, this is how they would define the dual. And you could get this from this, or vice versa. We get this from this. It doesn't matter. So I prefer to remember this because linear programs are usually defined in standard form. Okay, and we're going to see how do you get from, for example, this to this in a moment. Okay, so the first thing is that the first fact that I want to prove is that the dual of the dual is the primal. In other words, the definition gives us a dual of this program. But how about this now? This is a linear program. What is its dual? Well, this fact here say if we try to find the dual using this definition, we're going to find out that it's this. And let's do that. Okay, so the max. So we're going to start from here. This is now our primal. So the max, we could replace it by the min. The max is equal to minus the min of minus, right? it's trivial. And then y unrestricted, I could write y as u minus v, where u is greater or equal to 0 and v greater or equal to 0. So we replace y by two vectors, u and v, and both of them now are restricted to be greater or equal to 0. If y is negative, then u equals 0, v, it's v. If y is positive, then v is 0, and it's here. So this is an equivalent form. And then here, less or equal to, I'm going to change it to equality by adding a vector here, which is greater or equal to 0. So less or equal to, we're going to replace it by equal, but we're going to add plus w. Okay? So that's what we're going to do. So the max becomes the min of minus yb, so minus this. So minus u times minus b, right? Plus v times b, all right? And then ya, so that's u times a minus v times a, right? And then I add the w, all right, plus w equal to c transpose, okay? And then here everything is greater or equal to 0. So u is greater or equal to 0, v is greater or equal to 0, and w is greater or equal to 0. All right? So now it's in standard form. So I could even further do the min, and I just do the transpose. So it's minus b transpose times u transpose plus b transpose times v, and then here a transpose times u minus a transpose times v equal to plus w transpose equal to c, with u, v, w all greater or equal to 0. So this is the same thing. Now we have a linear program in standard form. Okay, so we're going to use our definition. So what you have to do is create a variable for each equation in the dual. Each equation is corresponding to a variable there. So here we have to have a variable corresponding to each equation. So let's call it h. So let h be the dual variable. Okay. So h is now going to multiply on this side, right? Let me call it h transpose. Okay, so h is a row vector, is a column vector. So h transpose is a row vector. So it multiplies, first of all, in here. So it multiplies the matrix this way. So h transpose times a transpose, right, is less or equal to this one, is less or equal to minus b transpose. Okay. And then h multiply the same thing, minus h transpose times a transpose, less or equal to, and its corresponding value b transpose, right? And then here also h, here is just the identity matrix. So h is less or equal, there is no w here, so it's 0. So h less or equal to 0. And then here I'm maximizing, all right, maximizing h transpose times c. Right? So if we let x equal to, see, this is h is less or equal to 0. So I'm going to set x equal to minus h. All right. Then we just replace. So I got here maximizing C transpose X, but there is a minus, so that's min. So that's min C transpose times X. All right. And then this one here, you see you got H transpose A transpose less or equal to minus B transpose, and its minus is equal also to, it's greater or equal to minus. If you put a minus here, so that will be greater or equal. So therefore, this is equal to B transpose. H transpose, A transpose is equal to minus B transpose. And because we're replacing X by the minus H, so I'm going to get A times X equal to B. And of course, X is greater or equal to 0. And this proves our fact that the dual, this is exactly the primal. So we proved that the dual of the dual is the primal. So now, like earlier when we have another formulation of this of the linear program, we said this is the technique that you use. If you are given any linear program, you got a max here, you got a set of equalities, inequalities, greater, less or equal to, and then here the x is not always restricted to 0. Some of them are, some of them are restricted. So you use this technique. So the max, if you had a max, you just replace it by minus the min of minus what you have, and therefore maximizing is equivalent to minimizing this. And now a variable that is unrestricted, you replace it by two variables, u and v, u greater or equal to 0, v greater or equal to 0. And finally, less or equal to, you add a variable called w to make it equality. And the same thing for greater or equal to, you replace it by minus w, right? You minus to make it minus w equal, right? So these are the technique to transform any linear program and to find its dual. But I personally prefer remembering this and knowing how to get to the dual instead of remembering every rule to find the dual. Okay, so now that we define the dual of the dual is the primal, let's state the first theorem on duality. Okay, and that's called the weak duality theorem. So theorem, this is called the weak duality theorem. Okay. And it says the following, that for every x such that a dot x is equal to b, x greater or equal to 0, so x is a primal feasible, then C transpose x is greater or equal to the objective over there, y times b, for every y such that y dot a less or equal to C transpose. That's what the weak duality theorem said. If you have a basic feasible solution to the primal, not a basic, but any solution to the primal, and a solution to the dual, in other words, feasible solution satisfying the constraint y a less or equal to C transpose, then the objective is greater, the objective of the primal is greater or equal to the objective of the dual. This is an interesting theorem because what it says is, if I know a single y such that ya is less or equal to c, then I have C transpose x greater or equal to yb for every x feasible. So my minimum this is now a lower bound. So my minimum can be only greater or equal to that value for anyone, and vice versa. If I know 1x satisfies ax equal to bx greater or equal to 0, then this C transpose x becomes an upper bound on this on all the solution of the dual. Okay, so that maximum cannot go to plus infinity. Okay, so if we have to, let's do a tableau here. So I'm going to put the primal here. And the dual here. And the primal could be infeasible, all right, unbounded, and optimal. Right? We saw that in when we did this when we did the simplex algorithm. There are 3 states for a linear program, and the dual is the same thing. It is so it could be infeasible, unbounded, and optimal, and that's the dual. Okay, so the weak duality theorem say if my dual is feasible, that is, I know a single y that's at ya less equal to C transpose, then this becomes a lower bound on C transpose x. So this min cannot be minus infinity. So if my dual is feasible, that means it's these 2 rows. Okay, so I cannot have the primal unbounded. So this is a no. All right. Okay, because it represents a lower bound. And then if the primal is optimal, that means it has a feasible solution, then I cannot have a no here neither. Okay. All right. Because these two rows, the dual is feasible. So I cannot have unbounded. Okay, here. And the same thing. This matrix is symmetric, so this is no also. Now, can I have infeasible and infeasible? Yes, because, for example, I'll give a simple example. So minimize minus x subject to 0 times x equal to 1, x greater or equal to 0. All right? So this is infeasible. If you go to the dual, it's maximize y, right? That's 1 here, subject to 0y less or equal to -1. So here the dual is also infeasible. 0 is not less or equal to -1, and here 0 is not equal to 1. So infeasible, possible. I'd say yes. Okay. So this is just right away we can tell, we can fill in these boxes from the weak duality theorem. Now, let's prove this theorem. It's so the proof is trivial. What is YB? Y times B. That's equal to, B is equal to AX, so that's Y times A dot X, which is equal to Y times A times X. Okay? But YA is less or equal to C transpose. and x is greater or equal to 0. So this expression here, what I'm doing is I'm multiplying by x each equations and then adding them up. So it's going to be less or equal to ya is less or equal to C transpose times x. And that's it, the proof. So here's a fact, direct corollary to this. So fact, if x star primal feasible and y star dual feasible, all right, and C transpose x star equal to y star b, right? So that means the objective of this is equal to the objective of that. Then x star primal optimal and y star dual optimal. Okay, it's this fact is trivial because we said this is a lower bound, right, on the objective of the primal. So C transpose x is greater or equal to this y star b, which is equal to C transpose x star. So C transpose x is greater or equal to C transpose x star for every x such that ax equal to b x greater than 0. So x star is optimal. Okay, so whenever you have two feasible solutions satisfying the constraint of the respective program, and if the objective function are equal, then those two are optimal. Okay, now let me fill in two more boxes here. Feasible. So for example, this one here, minimize 0x, minimizing x, subject to 0x equal to 1, x greater or equal to 0. All right? So this is infeasible, right? Obvious. 0 is not equal to 1. And the dual of this is maximize y, right? It's 1 here, so maximize y, subject to 0 times 0 less or equal 0 times y times 0 less or equal to 1, right? And y unrestricted. Okay? Well, this inequality is trivial. 0 is less or equal to 1. So any y is feasible. So this max is equal to plus infinity. So here I have a case of a primal infeasible and the dual is unbounded. So it's this box right here. Primal infeasible, the dual is unbounded. So I say yes. Okay? And now this matrix is symmetric, so I should have also a yes right there. In other words, I could have my dual infeasible, but my primal is unbounded. That is, the minimum is minus infinity. Okay. So we are left with this column, optimal and optimal. And that is, to fill those boxes out, we need what is called the strong duality theorem. So theorem, this is called the strong duality theorem. And it goes as follows. If x star is primal optimal. Okay, so we know that this program has an optimal solution X star. Okay, then the dual has an optimal solution Y star, I'll call it Y star, okay, such that C transpose X star is equal to Y star B. Okay, so if this has an optimal solution X star, then that problem over there, the dual, has an optimal solution Y star, and C transpose X star is equal to Y star B. So the strong duality, in the weak duality theorem, we have greater or equal. So the duality theorem close the gap and say when they are both optimal, the objective are equal. Okay, so in this tableau here, we can fill it up now. So if I am optimal, the primary is optimal, I cannot have this. So this is a no. And of course, this is a no also. It's symmetric. So only one box here. Then both are here. I call it yes. And C transpose X star equal Y star B. All right. So there's only one box here in this. They're both optimal and their objective are equal. Okay. So this is the strong duality theorem. And let's prove that. And we're going to prove it from the simplex algorithm that we studied in my previous video. So let's look at this problem here. Let's write it in Tableau format. So here I have A. Here I have C transpose. Here 0, here -1, right? And then B. And here -0. So this is our input for this problem. It goes like this, right? And remember when we did the simplex, so phase 1, phase 2. So here we are assuming that the problem has an optimal solution. So we did phase 1, the problem is feasible, and then we went in to phase 2, and then we obtained the final simplex tableau. A bar, that's 0, that's B bar, and then my C bar right here, C bar transpose, this is -1 minus theta bar. Okay, and this is the final simplex tableau. Right? And here I have B. Remember B, the basis matrix. And beta, the BFI. Right? It tells me where the basic variables are. By the way, in here, we can assume that X star is the solution obtained here. It doesn't matter, okay? Because here it doesn't say that it's a basic feasible solution. So it could be that this X star in this theorem is not a basic feasible solution. But for the sake of for the theorem, we could have said, X star is a basic feasible solution, and then what follows. So here, this is the basis matrix. Of course, at the end of the simplex argument, we have the basis matrix and the BFI. And I remind you what the formulas are: A bar is equal to B inverse times A. B bar is B inverse B. And C bar is equal to C bar transpose is equal to what we get here. It's C transpose minus C beta transpose B inverse times A. Right? And the solution X star, we set the basic variables equal to the right hand side is equal to B inverse B right, and then X star of beta bar equal to 0. Right? We set the non-basic variable equal to 0 and the basic variable equal to the right hand. That's what we get at the end of phase 2. Okay. Now, this is the simplex. This is the final simplex tableau, right? We stop, the simplex algorithm stopped here. What does it mean? That means C bar is greater or equal to 0. So C bar transpose equal to C transpose minus C beta transpose B inverse A. This is greater or equal to 0. If we had a negative number here, we would have pivoted on that one. So this is greater or equal to 0. So if I let this and I called it Y star, so it's a row vector, then what do I have? Well, I have Y star times A less or equal to C transpose. Right? So Y star is feasible. It satisfies the constraint of the dual. And now let's compute the objective function. What is C transpose X star? Remember, X star, X beta bar is 0, so it's just C transpose of beta times B inverse B. Right? Because X beta bar is 0. And this is my Y star, so this is equal to Y star B. So the two objective functions are equal. And because of the previous corollary to the weak duality theorem, Y star is dual optimal. Okay? And that concludes the proof of the strong duality theorem. Now, remember, I am assuming here that A is of the same size as this A. But remember, at the end of phase 1, sometimes we deleted some rows because they identify a redundant constraint. So I leave it as an exercise to figure out what to do in that case for this theorem to still hold. We just have to augment this Y star we get here by zeros corresponding to the redundant constraint. So I urge you to go back to phase 1 and see what all the condition that we end up with at the end of that phase, and see how you can fit it here. But if at the end of phase 1 we eliminated all the basic artificial variable, then this is good. All right? A bar is the same size of A and everything is correct. But you have to also figure out what to do in the case they are redundant constraint and so forth. So this is the strong duality theorem. And now we filled out every box in this diagram here. So when one is optimal, the other one is optimal, and then the objective function are equal. Now, continuing on this, there is also a very important theorem. It's called the complementary slackness, and it is used to devise algorithm based on that theorem. And in my next videos, we're going to see what's called the Kilter algorithm, and the Kilter algorithm devise it's an algorithm based on the complementary slackness that I'm going to state right here. So okay. So if I have X star primal optimal, primal feasible, not optimal, and Y star dual feasible, then I have this equivalence. C transpose minus Y star A times X star is equal to 0, is equivalent to X star optimal and Y star optimal. Okay? And the proof is very trivial. So let's look at this expression here. Remember, YA is less or equal to C, right? So this vector is greater or equal to 0. And I am multiplying it by a vector that's also greater or equal to 0. So it's a sum of numbers greater or equal to 0. And that's equal to 0. So every term is 0. In other words, if I look to the ith term, that's what? That's Ci minus Y star times A dot I, the ith column, times Xi is equal to 0 for every I. That's what this means. Okay. And another way of saying it is that if Xi is positive, then this is equality. So Ci is equal to Y star times A dot I. So X star. So if my solution is X star I is equal to 0 and it verifies this, that is, the ith equation here is not less than C star, it's equal. Okay? So that's what this means. Okay? Now, so if I have this expression, then that implies X star and Y star is optimal, and vice versa too. If X star is optimal for the primal, Y star dual optimal, then we have this. And the proof is so trivial. Let's calculate what this is. C transpose minus Y star A times X star. That's equal to what? That's equal to C transpose X minus Y star AX star. Right? Which is equal to C transpose X star minus Y star, and now AX star is equal to B, so that's B. So what this says is that if we go that way, so if x star are feasible and the two, this is now is equal to 0 and the objective are equal, then they are optimal. We just saw it in the corollary to the weak duality theorem. And then when we proved the strong duality theorem also, we said when both of them are optimal, the objective function are equal. And if the objective function are equal, this is 0, and that implies this. So that's why I said the proof is so trivial. Now I'm going to switch to an Excel session where I'm going to take a specific linear programming problem and programming the simplex using Visual Basic and show the different phases of the simplex algorithm and all the things that we discussed in the previous section, like degeneracy, how do we handle degeneracy, lexicographic method, redundant constraint, all the possibility in phase 1, and then at the end, how do we come up with the optimal solution.
This is a linear programming example that illustrates all the results that we covered in my previous video, like phase 1, phase 2, degeneracy, lexicographic method, and the duality. So this system here, so I have a system of equation a dot x equal to b. This is A matrix, this is B, and x is the decision variables, and x is of dimension 7. And here we are requiring that all the decision variables are non-negative, and then I have a unit cost here, and I want to minimize C transpose x, where C transpose is this vector. So it's just the sum of this unit, for example, this one times x1 plus 2 times x2 and so forth. So that's the problem we want to solve. Now, the simplex algorithm requires a starting simplex tableau, and here we don't have it. So we're going to use phase 1 to do that. So I'm going to bring in the phase 1 linear program that we're going to solve. So I'm going to say initialize. So I have a program here that's going to initialize this. So here's the phase 1 linear programming problem. So we want to, my set of equation is a dot x plus iw equal to b. I is the identity matrix. So here we are adding an artificial variable w for each equation. So this is plus w1 plus w2 and so forth. So this x and w must satisfy this system of equation. Both x and w are greater or equal to 0, and I'm going to minimize the sum of this variable, sum of the w's. So that's just E transpose w. So this is the linear program of phase 1. It's different from the previous linear program, but this one will help us find the simplex tableau for the problem that we are concerned about. So, and we saw that that if the minimum, first of all, w is greater or equal to 0. So this is E transpose w is greater or equal to 0. So 0 is the lower bound. And also this system of equation is feasible because I could set x equal to 0 and w equal to b. So here we have a linear program. The solution space is non-empty, and the minimum is bounded below. It cannot go to minus and infinity, which means that this program has an optimal solution. Okay. So after we solve this program, if the minimum is strictly positive, we saw that that means that our initial problem is the solution space for this problem is empty. Okay, so there is no need to optimize. But if the minimum is 0, then this problem, our original problem, is feasible, and we need to optimize this cost function. So let's initialize in a Tableau format this program here. So I have a program here that's gonna initialize this. So I click on that, And so this, we're going to put it in a tabular format. So here goes A, the A matrix. Here goes the identity matrix for the W. So these columns are the W columns. And then the right-hand side. Same thing as B. Now here, this is a copy of my cost function before. And my cost function doesn't depend on the W, so it's 0 here. And then here I put -1 and here zeros. So this equation equal to 0. So this equation just say that this variable Z is equal to C transpose X. So just to make the objective function in an equation format. And here, this is objective of phase 1. That's E transpose W. So it's 0 under the X's and 1 under the W's. And then here also, same thing. The W objective is equal to E transpose W and equal to 0. So my problem here in tabular format, it looks like this. So again, here also we need a starting simplex tableau. But here it's obvious what it is. So it's here are my basic variables. The right-hand side is greater or equal to 0. The only problem is I have here is that, remember that in a simplex tableau, the coefficient in the cost vector has to be 0 for the basic variable. So we need to cancel this vector of 1s. So what we do is we do this row here minus the sum of these rows to cancel this, and that gives us this tableau format. Okay, so this is my basic, so it says B on top of it. So these are my basic variables. This is the right-hand side, it's greater or equal to 0. And C, the coefficient under the basic variable is 0. Note that in phase 1, we really don't need this row 25. We need that in phase 2. Okay, but we keep a copy of it. Okay, so now, so that's my program. Now, remember that there may be degeneracy of this in this program. So what we do is we add the identity matrix here, and we'll do the lexicographic method. So you see every row here is lexicographically strictly positive. All right, and we're going to keep it that way. In other words, what we are really doing is adding an epsilon here. Okay, 2 plus epsilon, 2 plus epsilon squared, 10 plus n cubed, and so forth. And we are solving the problem for epsilon positive small. Okay, we've seen the equivalence between the lexicographic problem with the epsilon problem. Okay, and of course here the BFI, it's important to keep track of, is the basic feasible index. In other words, what are the indices of the basic variable and which row they occur on. So here obviously it's these, so that's 8, 9, 10, 11, 12. Okay, the 8 appears on the first row because I have a 1 here. Okay. So this is a simplex tableau for phase 1 problem. So now we're going to start using the simplex algorithm to solve this. So what simplex does, it chooses in this row here, it chooses the most negative number. So in my case, it's -10. So this will be my first pivot column. And then we're going to do the ratios, right, to maintain the lexicographically positive of this row. So we're going to do, first we're going to do the first one. So we're going to do 2 divided by 1, 2 divided by 1, 10 divided by 1, 4 divided by 2, and 10 divided by 5. So when I look to this column, there is a 4-way tie. Row 1, 2, and 4, and 5. They all tied with a minimum of 2. So that's why this problem here is degenerate. Okay. So now, to break the tie, we're going to use the lexicographic method. So what we do is we take this row here, we divide it by 1. We take this row divided by 1, take the 4th row divided by 2, and then the last row we divide it by 5 up to here. So I have 5 rows which are lexicographically strictly positive, and I'm going to find the lex min. And here it's obvious that it's this row here, because it has all zeros, and then at the end, it's this row, I'm sorry. It's this row here. It has all zeros and then 1 here. So I'm going to execute the program that finds the pivot. So it's going to do all this calculation for us. So find the pivot, and indeed it finds that we have to pivot in here. Okay, so I'm going to pivot. Okay, so now this is becoming basic. So you got 0, 0, 0, and 1 here. And then I'm going to ask it to find the next pivot. So we're going to pivot in this column because minus 12 is the most negative number here. Okay, so I'm going to pivot here again. And then I'm going to find the pivot again. I'm going to find the pivot. And I am done. So this is the final Simplex tableau for phase 1. And it is the final Simplex tableau because there are no negative number in this cost vector. Okay, so we are optimal in this case. Now, remember that our objective was to find Simplex tableau for this, but we don't have it here at the end of phase 1. We don't have it in here. Why? Because I still have 2 artificial variables in the basis. Okay, so 8 and 9 are in the basis. And we were not able to get rid of this artificial variable. We were hoping that at the end of phase 1, the only basic variable I have are the x column, in the x columns. But here we don't. So therefore, if we look to the lexicographic phase 1 problem, right? So here, the optimal objective, the lex min, is equal to minus this row. Okay, and this row minus this row is lexicographically strictly positive because it's going to start with a 1. So the lex min is strictly lexicographically positive, which means that this problem here, if I attach the identity to it and solve it lexicographically, the problem will be infeasible. The solution space will empty. We've seen that. Or the epsilon problem. So if we perturb these, like 2 plus epsilon, 2 plus epsilon squared, and so on, 10 plus epsilon to the power 5, where epsilon is a very small positive number, first, this program is non-degenerate. And 2, when I solve it, I'll find it to be infeasible. So that's what this tells me. Okay? But how about the regular simplex problem that I have here? Well, we look here, in this entry right here. That's the minimum. That's this minimum here. It occurs right there, and it's 0. So therefore, my original problem is feasible, and I better come up with a simplex tableau in order to optimize it. Now, remember the goal of phase 1 is to find a starting simplex tableau for this problem. And here, right now, it's not a simplex tableau for this problem because we have these 2 artificial variables in the basis, 8 and 9. Those are artificial variables. So what we do is we look at the area facing those artificial variables. In my case, they are the first 2 rows, but in general case, they could be anywhere within the A matrix. Now, let's assume that this number, for a moment, this number is non-zero. It's either positive or negative. What if we pivot there? What happened? Well, remember the minimum is 0. So what's facing those artificial variables are all 0. This is 0 and this is 0. So if you pivot here, And because this entry is 0, it's not going to change the yellow area. It's still going to be the same, and of course it's going to be greater or equal to 0, which is a requirement in a simplex tableau. And also, if you pivot there, you will get rid of this artificial variable. So this artificial variable is going to leave the basis, which is good. So we replace a basic artificial variable with an X column. And then this basic artificial variable is still going to be there. So we're going to look at the area facing that one. And then if there is, in my case it's all 0, but let's assume this is, now it's a non-zero entry. So it's either positive or negative. Then I pivot the same way. I have a 0, so it's not going to change that. And then I will get rid of this basic artificial variable. And then after I do that, then I have a simplex tableau for my original problem, because now all the basic variables are in the A area, the A matrix area. So now, if there are still basic artificial variable left, then the area facing them should be all zeros. Right. We have pivoted on all the positive or negative in those areas. So what does it mean? So if we set this W equal to 0, so this column are multiplied by 0, what do we get? We get 0 times X equal to 0. And same thing for the second equation, 0 times X equal to 0. That's they are called vacuous equations, and 0 times X is obviously 0. So these equations are not really needed in the optimization that I am going to do. So, and what does that mean when we have all zeros facing the artificial variable? Phase 1 has identified, in my case here, that these two constraints can be obtained by a linear combination of these constraints, of the last three. So they are redundant constraints. They are not needed to optimize this my cost function. So we could do one of two things now. We could leave the system as is, delete the last row. We don't need it. That's phase 1 objective. We don't need that. And then flag these columns so that we never select them as a pivot column. Even if we see a negative number here, we are not going to choose that as a pivot column. We're just going to pivot on column corresponding to this green area under the A matrix. And we continue that way until we reach optimality. The only caution I have is that when you do this, remember when we looked at this area here and saw a negative number or positive number, let's say here, we force the pivot there. So what that means is that this area here may no longer be lexicographically positive. And that's okay, because we could, at the beginning of phase 2, attach an identity matrix next to it. And then we will use this vector here, the B vector, and the area which we just added to break the ties when we do the pivot, if there is degeneracy. Okay, that's how we can do this. Or the next method is, well, this is just 0x equal to 0, so I don't need these two rows. I don't need the artificial variable, so I'll delete this. And I delete the bottom row. And I delete this column here. That's just for the phase 1 objective. And then I delete these two columns because they correspond to the basic variables, the artificial basic variables. And then we end up with a system which I have a function here. I'm going to black them out, those areas. And we are left with this. Okay, so I deleted everything I don't need, and now this is a simplex tableau for my original problem. Okay, and then we continue as like the simplex algorithm. And of course, the only caution I say also is at the beginning of phase 2, we need to make sure that this is lexicographically positive to break the ties when we do the pivot. If it's not, then I will just add a matrix here of the identity matrix, and then use this along with this new area to break the tie in case there is degeneracy. And in here, so my matrix on phase 2 is no longer 5 by 7. It's only 3 by 7. This is the C vector, and this is that 0, 0, minus 1, the Z variable. And then this is the right-hand side. And in here, this is B inverse. All right? For the column 3, 4, and 2. Okay? So here it is a simplex tableau for my original problem. Okay? So now we move to phase 2 with this. So if I do find pivot, then it's going to tell me, okay, this is now we are into phase 2, which are minimizing our original problem, minimum Cx, Ax equal to b, x greater or equal to 0. So here's my cost vector, all right, and I choose the most negative. So this is my my pivot column. So I say find the pivot. So it's found this pivot here, and it's gonna pivot in there, and then I still have negative number there. Find the pivot, it's right there, and then pivot, and that's it. My cost vector is greater or equal to 0. Therefore, I have found what the optimal solution is. Okay, so here's the optimal solution. It's all zeros except for the basic variable. So we look here. The variable 7 is on the first row. On the first row, so it's 5, right? That's 5. Then the x4 is in the next row, which is 3. So x4 is 3. And then x1 is on the last column, which is 2. So this is my optimal solution that I was seeking in this problem here. So let's calculate the objective function. So that's equal to matrix multiply of C transpose. This is my C transpose, comma, and then the x. It's minus 44. That's the optimal, the best cost I could have. And look where it is. It's right here. It's under the B column. So this entry here is minus C transpose X. So you take this value and minus that. That will be your optimal objective value. So let's verify that it's feasible. So this equal to matrix multiply of the A matrix, comma, times the X, and indeed it's equal to the right hand side, 2, 2, 10, 4, and 10. So this solution is feasible, okay, with an objective value of minus 44. Now the simplex also gives you the value of the optimal dual variables. Where are they? It's minus these values under the inverse matrix. So this is equal to minus this. Okay. And then I'm going to fill in 0 here and 0 here. Why? Because we deleted 2 rows, right? So I'm just going to put 0. Okay. So this is my optimal objective function, optimal dual variable. Okay. And let's first of all see if that satisfies the constraints for the dual. Remember, the dual is y star a is less or equal to c. So let me do matrix multiply of this, comma, and then the A matrix. So that's that. And I'm going to have a copy of my cost vector to put them side by side. Let's see. And here you see, indeed, this vector is less or equal than this vector, right? 1 is less than 1, minus 6 is less than 2, minus 14, and so on, okay? So this equation are satisfied. So this dual feasible solution, this is a dual feasible solution. And then the objective function of the dual, remember, it's B transport Y star. So I'm going to do MMULT of so Y, comma, and then the B. It's minus 44. So you see you have a feasible solution of the primal with objective function minus 44. You have a feasible solution to the dual with objective function minus 44. Since the dual objective function is equal to the primal objective function, both of these are optimal for their respective linear program. And we are done. So remember that the simplex also gives you the value of the dual variable. They will be under the B inverse. Okay. How about the complementary slackness theorem? Well, it says that whenever an entry to the optimal solution is positive, then the corresponding constraint in the dual must be equality. So, for example, this is positive, the first one. So the first constraint, which is this, is an equality, and instead 1 is equal to 1. Now here the fourth one is positive, so the fourth, 1, 2, 3, 4, the fourth is equality, so 3 is equal to 3. Finally, the last one, that's positive, so the last constraint in the dual is equality, so minus 11 equal to minus 11. So this is also, of course, it should satisfy the complementary slackness that we reviewed. So in case you may want to program the simplex algorithm, let me comment on a few things. First, the minimum data that you need from an iteration to the other is the inverse of the basis matrix, which is right here. We need to know that. And also the BFI, the list of order indices where the basic variables are. So that's the only thing that you need to know, because the blue area here, A bar, we call it A bar, it's B inverse A. The yellow area is B inverse B. And then the green area, that's C bar, that's C minus C beta B inverse A. So these are the formula for a simplex tableau. Okay. So when carry out the computation, first, at the beginning of the iteration, you have to compute what C bar is. Well, C bar is C minus C beta B inverse A. So, and it so happened that the minus C beta B inverse is this red area. Okay. So in addition to knowing the B inverse, it's a good idea to keep track what this is. That's the row below the inverse of the basis matrix. And then your C bar is just C plus this vector times the matrix A. And now, knowing now C bar, that is, you have computed what this green area is, now you have to figure out the pivot column. So you're going to choose the most negative number in this green area. Right here, I am in the optimal situation. I don't have one, but let's assume it's this column here. So this is my pivot column. So I'm going to need to know what these values are. But what is that? That's 1, 2, 3, 4, 5. That's the fifth column of A bar. So I go here, the fifth column of A bar is just B inverse times the fifth column of A. So I do that calculation. So now I have then everything I need to know in the pivot column. And also it's a good idea to keep track of this column also. So we don't need to redo the calculation every time. So now you got the pivot column and you got the right hand side here. Okay, and then you just do the pivot as if you only have these. You have this column and the right hand side, and that will update for you this column. Okay, and update the basis matrix, and you update this the red vector, and also you update your BFI. Let's say I decided to pivot on this element. So I'm going to replace this 4, the second row, by the index of the column, which is 5. So this 4 becomes a 5. And now I have everything I need to move on to the next iteration, and so forth. So that's the basis of the revised simplex algorithm. So you don't need to know everything in this matrix like I did with my program. I recalculated things that I really don't need. Okay, so you keep track of this column and then this matrix right here, and of course the BFI. And this cell here, it's optional if you want to keep it or not. That's just the value that's minus C transpose of X bar. All right, you can keep track of it. So that's the end of the lecture on the simplex algorithm. Now the next phase, my next videos, the first one is going to be on matrix game and its relationship with linear programming, and then we're going to prove the famous theorem called the minimax theorem. And then what follows is network flows. We're going to use our results from duality and so forth to solve the max flow problem and then the minimal cost circulations. And finally, the last video would be on Karmakar algorithm. And then we're going to go through the proof of convergence, and then we end this series on the linear programming.